Welcome to UGC EPG Pathshala. Hello, I am Dr. Anshu, Associate Professor at Department of Geography, Kirori College, University of Delhi. I will talk to you about the models in geomorphology. Let me first introduce why are models important in geography. Like any other discipline, model building in geomorphology plays a very significant role. This was very vividly highlighted by various geographers. The progression of abridging real landscapes to manageable proportions is model building. Defined in a general way, a geomorphic model is a simplified representation of some aspect of a real landscape that happens to interest a geomorphologist. It is an attempt to describe, analyze, simplify or display a geomorphic system. Model building in geomorphology has been strongly influenced by the systems analysis, and system approach is most suitable to provide insights and make predictions. The dynamics of different systems are explained by these geographic models, and three major construed systems in geomorphology are identified as the natural analog system, the physical system and the general system. Let us now understand each of these construed systems individually. First, we talk about the natural analog systems. One of the most widespread methods of illuminating a given geomorphological phenomenon is to interpret its significant or characteristic features through some analogous natural system that is believed to be easier, better known or in some difference more voluntarily observable than the original. By such reasoning, we see how classifications, which means that like objects are grouped together for the purpose of making some general statements about all of them, outline a fundamental part of one type of model building. There are two classes of natural analog systems, the historical and the spatial analog system. What are historical analogues? These collectively explain geomorphic phenomena with respect to their assumed positions in time controlled sequences on the postulation that what has happened previous to the current situation will happen again, or that what existed in the past and had application and importance then has relevance to what exists now. Consequently, the phenomena under reflection is viewed as part of a progression of real, individual but interrelated events. It is after all the strongest instructive motor of geomorphology that past landscapes can to a large extent be entirely understood with reference to the present ones. Wills in 1929 has efficiently used analogies with present deserts and illustrates and gives details of late Carboniferous and Permian landscapes of Britain. From another point of view, it might be argued that present landscapes can be better understood with reference to past ones, and recently Ambrose has suggested that the sedimentary stripping of the sub-Ordovician paleoplain of the Canadian Shield is reactivating an ancient topography that is practically intact. The other class of natural analog system is spatial analogues. The spatial analogues connect one set of phenomena with other on the assumption that observations at another place are easier to make or simpler in character than those of the preliminary, or that resemblance with other areas believed to be in some way analogous will allow one to make more confident and meaningful generalizations about the original area. It is in this last sense that the classificatory character of this segment of model building appears most clearly. The most widespread form of spatial analog model is that in which adjacent flanking areas are grouped together on the assumption that each unit can be understood in terms of generalizations about some larger region of which it forms a part. Consequently, on the continental scale of morphotectonics and on the regional scale, for example, structural geomorphology, individual landforms are grouped into tectonic or structural provinces. An additional type of geomorphic spatial analog is the so-called natural model, in which what are believed to be characteristic assemblages of landform units are identified and presented as type assemblages. Now, the second construed system in geomorphology that we talk about is the physical system. The physical system approach is most perceptibly associated with conventional scientific method and was the first to be applied to quantitative data in earth sciences, particularly in the 1930s and 1940s. This approach is based on the view that research can best be pursued by dissecting the geomorphic problem structure into its component parts, such that the operation of each part and interactions between parts can be pragmatically examined, showing the way to a full synthesis of the components into a working system. It is expedient to divide the physical system investigations into three often interrelated types: those in which the significant structural elements are substantiated into a hardware model, mathematized into a mathematical model, or subjected to field observation under some expedient experimental design. Now, we will examine each one of these three models of physical system in detail. First, we discuss about hardware models. It has been seen that geomorphologists, like all scientists, construct models at various levels of abstraction. The most primary level requires a modification of scale. In this case, a hardware model represents the system. There are two main kinds of hardware models: scale models and analog models. The most precious hardware models have been those which were, on the whole, parts of unscaled reality, tightly constrained and examined in great detail. The two most obvious instances of this are Bagnol's wind tunnel observations on sand movement and Schum's investigation of the erosional forms and transformation of the Perth Amboy Badlands in 1959. This gives the inkling to the indispensable complexity of the construction of hardware models in geomorphology, that the complications of nature compel scaling of changes of media requirements of a very high order of complexity. It is accordingly easier for an engineer to replicate a life-size human-made structure than for an earth scientist to invoke a natural complex. Scale models are almost accurate replica of a section of the real world, which they bear a resemblance to in some very palpable respect, and the similarity may from time to time be so close that the scale model becomes simply a rightfully controlled portion of the real world. The most understandable geomorphic benefits of the use of scale models area are the elevated level of control which can be achieved over the simplified experimental conditions and the manner in which time can be compressed. The wide-ranging problems of scaling and of dimensional similarity have been comprehensively treated by Murphy, Wilson, Duncan, Langhar, and in particular references to earth science by Hubbard and Strahler. The major issue in scale models is that the changes in scale affect the relationships between certain properties of the model and the real world in various ways, such that, for example, the kinematic scale ratios perform differently from linear scale ratios. Identical difficulties are involved which attempt to produce meaningful dynamic scale ratios. Such disagreements can be generally avoided in any of the three interrelated ways. Firstly, a deformation of one significant attribute can be reduced or eradicated by distortion of another attribute. For example, a deformation of the vertical linear scale of river models enables the effects due to turbulence to be more or less faithfully reproduced. The second and the most significant way in which analogous model ratios can be fashioned is by dimensionless combination of attributes. Consequently, a combination of density, velocity, depth and viscosity permits gluey effects to be perfectly reproduced, and a combination of velocity, length and acceleration of gravity is important where gravity effects need to be accurately scaled in the model. Thirdly, one or more of the medium can be changed in the model to aid the true scaling of other effects, but such considerations naturally lead one into the second type of hardware model, the analog model. Problems of scaling natural geomorphic phenomena give details the malfunction of attempts to reproduce entire fluvial landform associations and their transformations, and why the most successful work has evolved attempts to reproduce restricted features like river meander bends and beach segments. Now, what are scale or iconic models? These are diminutive or every now and then extremely large copies of systems. They may be at variance from the systems they represent, merely in terms of size. Relief models, which are made out of a suitable material such as plaster of Paris, have been used to symbolize topography as a three-dimensional surface. It is not necessary that scale models have to be static. Models fashioned by utilizing material similar to those prevalent in nature, but the dimensions of the system scaled down, can be utilized to kindle a behavior that is not static. Other scale models use natural materials, but the geometry of the model is divergent to the geometry of the system it replicates. The size of the system is scaled down by the investigator. The procedure of plummeting the size of the system possibly will create a number of uncomfortable situations with respect to scaling. For example, a model of the Severn estuary made at a scale of 1:10,000 can be no trouble conserve geometrical and topographical relations. On the other hand, when adding water, an actual depth of water, say 7 meter, is represented in the model by a layer of water less than 0.7 mm. In such a thin layer, surface tensions will cause massive issues, and it will be impractical to set a line, range and uniformly material scale down to represent. The real system would be so minute that a large amount of it would float. These issues of scaling are frequently surmountable to a definite extent at least, and scale models are used to imitate the behavior of an assortment of geomorphic systems. For example, scale models have assisted studies of dynamics of rivers and river systems using waterproof troughs and flumes, and supported studies of talus slopes. Analog models are further abstract scale models. Analog models engage radical changes in the medium of which the models is constructed. For the largest part, commonly used analog models are maps and remotely sensed images. On a map, the surface features of a landscape are reduced in scale and represented by symbols, rivers by lines, relief by contours, and spot heights by points. remotely sensed images like aerial photographs and satellite imageries represent specific properties of landscape systems at a reduced scales. Maps and remotely sensed images are apart from where a series of them is offered for different times static analog models. Dynamic analog models may also be built. Now, I will present the second type of model in physical system, which is the mathematical models. A mathematical model can be defined as an abstraction as it substitutes objects, forces, events by an expression containing mathematical variables, parameters and constants involving the acceptance of a number of idealizations of variety of phenomena studied, and in assigning to the assortment of entities involved some austerely defined property. The indispensable features of the phenomena are then equivalent to the relationship between firm abstract symbols which can be written down. The phenomena in consideration bear a resemblance to closely something enormously basic with very few attributes. The resemblance is so accurate that the equations are a kind of working model from which we can forecast features of the real phenomena which we have never observed. The general type of geomorphic mathematical model is the one which concerns some simplified statement of definite significant features of the real world, which can be transformed according to assumptions concerning the fundamental operations of the system, yielding by checking the model forecast against the proper real world situations. Some information about the primary mechanisms engaged and the sequence of geometric changes to which the earth's surface experiences with the passage of time are integral to this model. Consequently, mathematical examination follows the symbolic statement of assumed primary static and dynamic relationships, and logical mathematical conclusions are then tested against real world, and the effects envisaged by model point towards the success which we have had in building the original model. The dissimilarities exposed then might lead to the unearthing of auxiliary causes, and those observed facts may be understood in greater detail. Mathematical models are frequently divided into categories like deterministic and stochastic models. Those based on classical mathematical notions of exactly predictable relationships between independent and dependent variables, that is, between cause and effect, are called deterministic mathematical models and comprise of a set of exactly specified mathematical assertions from which exceptional consequences can be deduced by logical mathematical arguments. Such models are very closely concerned with relationships and driving forces between factors identified in the simplified model. The most widespread type of deterministic geomorphic model engages transformation of slope profiles under a variety of assumptions. Let us see the second type of mathematical model, that is stochastic models. These include random components that permit different possible results emanating from given set of initial conditions. An example of stochastic model is one in which simulation of individual streams originating under varied conditions or forces operating at random link and form stream network. The third type of construed physical system is the experimental design model. In terms of contributions made to geomorphology, the foremost aspect of the physical system approach engages the understanding that within a given range of observational data lies definite, meaningful component parts that can be recognized by making use of a suitable experimental design. On the basis of the experimental design, constructed with reference to some conceptual model of nature of difficulty and appropriate operational definition of its component parts, numerical data is collected, checked with respect to their scalar and number system distinctiveness, and a data matrix is composed. This data structure is frequently analyzed by regression type statistical technique to construct a simple variable system in which workable correlations are acknowledged, engaging the course and strength of assumed causation. Let us now look at the most important and commonly referred approach in geomorphology, the general systems approach. The general systems approach to study of landforms rests upon some extensive attitude to group of geomorphic phenomena which is obtained as the consequence of experience or insight. For this reason, the prominence lies in the organization and operation of the system as an entire system or as linked components to a certain extent rather than in detailed study of individual system elements. A geomorphic system is then an inclusive composite of landforms which operate together according to some apparent pattern, energy and matter input into the system, giving rise to a predictable system response in terms of internal organization and consequential energy and matter output. Geomorphic systems can be regarded as part of the supersystems and as being comprised of subsystems. Subsystems are consequently the indispensable components of a system and can be acknowledged as distinct input-output linkages. In geomorphology, subsystems are generally united by pouring the output of one of the subsystems into an additional subsystem to form its input. When interest in the subsystem operations is extremely detailed, the systems approach is substituted by the experimental design model. Two systems are said to have similarity when there is precise equality of all components, and to have equivalence when they transform the same inputs into indistinguishable outputs. Synthetic system, partial system and black box are components of general system, and here we talk about them in detail. First, we see what are synthetic systems. Synthetic systems in their preliminary phases exhibit similarity with experimental design models, being involved with recognizing allegedly critical features of structure of geomorphic phenomena together with their sampling and analysis. The purpose of synthetic systems research, on the other hand, goes further than this, in that its objective lies in synthesis of analyzed structure and extension and generalization of conclusions to the point of making process response models. The modus operandi for building up synthetic systems starts with recognition of definite vital structural elements in a geomorphic complex, together conceivably with some views as to the potential relationship between these elements, involving direction of causation and which variables change together. Now, let us look at the partial systems. The partial systems are ones which have been first and foremost associated with resolving of fundamentally practical problems in the earth sciences. It has been related to establishment of workable relationships between often randomly grouped sets of factors or subsystems. Detailed knowledge of subject of internal functioning of these subsystems is not regarded as obligatory, but the attainment of precise information about interrelationships between these subsystems allows one to recognize and forecast the behavior of the entire system under different input conditions. This information may come from diverse sources, but object is always to set up mathematical relations between systems inputs and outputs without any effort to illustrate unambiguously the internal mechanisms of the system. The consequential behavior pattern are then used to envisage and to a smaller extent to comprehend the behavior patterns in other similar systems or in same system at different times. Lastly, we talk about the black box in the general system. On the whole, intense application of general systems models engages the concept of the black box. There is modest or sketchy information concerning the system components or subsystems within the black box subsystem. The interest is focused upon nature of the outputs. In geomorphology, black box approach has supported much of the significant work of the last 100 years. Such work has been characterized by broad perspective leaps wherein decisions are taken on the subject of supposed dominant characteristics of broad landform assemblages. Even though there has been much guesswork and assumption regarding detailed nature of the progression at work, the characteristic pattern of landform transformations through time and rates of operation of geomorphic processes. To conclude our discussion on models, we talk about testing the model. The testing of the patterns, relationships and process responses estimated by geomorphic models engages reappraisal against the real world conditions. Even though such testing is undoubtedly the generally significant single step in successful model building, definite types of models have proved more vulnerable to reappraisal than others. The most testable models are present in midst of the hardware, partial system and experimental design models. Engineering type hardware models are continuously checked against reality through construction to allow for adequate representation of present conditions. They are over and over again molded to known past conditions and as to their reproduction of known historical progression of events. And finally, forecasts from the model usually form the basis for engineering works, which themselves form expensive tests for the appropriateness of the model. In the same way, the building of partial system models engages the unvarying checking of real world inputs and outputs, so that concluding model can usually replicate a limited characteristic of reality with authenticity. Experimental design models can also be eagerly tested by collecting new data, which are statistically checked against the relationships resulting from the original model. To a certain extent, more difficult to test are the process response model, consequential from the synthetic systems approach and the mathematical models. This is because of higher level of generality presumed by these models and the complicatedness of unscrambling local complications from authentic errors in the model. With respect to deterministic mathematical models, little effort has been made to test their inferences in the field. Finally, let us say that the most difficult type of models to check are some of the natural analog system and the black box general system, since their construction in past has engaged such immense leaps into generality based upon decisions concerning the dominant system characteristics, the origins of which may be incomprehensible. Consequently, for example, definite denudation chronology models and the cycle of erosion engage so many built-in assumptions that any testing to which they have been subjected usually develops into circular reasoning. On the other hand, an example of a simpler type of black box model which received outstanding field support after 100 years was Darwin's theory of development of atolls from fringing and barrier reefs by the slow subsidence of reef foundations. This model was deductively supported by Davis after more than a few unsuccessful attempts to drill deep ocean trawls. To summarize, let us say that the reappraisal of geomorphic models is infrequently completely unambiguous, but checking, discarding and remodeling have got to become the center of geomorphic concern. As geomorphologists, we have to see that the discipline has to enlarge from a subjective catalogue of phenomena into a rational and cogent one. I thank you all for listening to this module on models in geomorphology and wish you happy learning.